Hey everybody. So we're going to get started with chapter 11. So section 11-1 is going to deal with sequences, and then everything after section 1 and excuse me, in chapter 11 is going to deal with series. Okay, so I'm going to break this up into two videos. I did a 45-minute video earlier this weekend, and my screencasting program like froze at the very end. So I'm going to break it up into two smaller videos because if there are any malfunctions, it's less frustrating to redo like a 20-minute video as opposed to a 45-minute to an hour video. Okay, so let's go ahead and start with the definition of a sequence. So a sequence, A sub n, which a lot of times is enclosed inside of set braces, is a set of elements or numbers written in a specific order. So you can think of a sequence as just being like a list of terms, usually separated by a comma. And the domain of a sequence is typically the set of natural numbers. So the set of natural numbers is like the set containing the numbers 1, 2, 3, 4, 5, and so on and so forth. You can think of that as like the set of positive integers. Okay, and in this lesson, we are going to be working primarily with infinite sequences. So there are three ways in which we can write a sequence. So the first way you'll see a sequence written is where the terms of a sequence are listed inside of set braces. So you have the first term represented by a sub 1, the second term represented by a sub 2, the third term is a sub 3. You're going to continue out to the nth term, and then that dot 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 at the end indicates that that sequence is continuing forever. The second way you'll see a sequence listed or written is where you have a formula, A sub n, that generates all of the terms of a sequence written inside of set braces. And then the third way you'll see a sequence represented will look exactly like number 2, except for you're going to be given a starting value, so a starting number to plug into your formula, which in this case is n is equal to 1, and then the infinity on top, that's going to give you the last number that you're plugging into the sequence. And we use the third way to write a sequence a lot of times if we want to start our sequence at some number that is not n is equal to 1. So if you want to start it like n is equal to 0, or n is equal to 3, or n is equal to 4, you'll see sequences represented by that third means. Okay, and that's what I wrote down below. Number 3 is typically used when our starting value is not 1. Okay, so let's do a quick example involving sequences where the directions ask us to write down the first 4 terms of the sequence. And then for this example, we're given the sequence generated by the formula n plus 1 over n squared, starting at n is equal to 1 and having infinitely many terms. So if we list the first 4 terms of that sequence, we're going to get the first term by plugging 1 in the place of n. So when we plug in 1, we get 1 plus 1, which is 2, divided by 1 squared. 2 divided by 1 is 2. The next term we're going to get by plugging 2 in the place of n. So that's going to make the numerator 2 plus 1, which is 3. The denominator is 2 squared, which is 4. The third term we get by plugging 3 in the place of n. So the numerator is 3 plus 1, which is 4. The denominator is 3 squared, which is 9. And then our fourth term we get by plugging 4 in the place of n. So the numerator 4 plus 1 is going to be 5. The denominator 4 squared is 16. And then I'm going to put a comma and then a dot 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 at the end to indicate that sequence is going to go on forever. Okay, now what we can also do is we can take the terms of a sequence and graph them. So if I take the terms of the previous sequence and then want to sketch a graph of what that sequence looks like, when you make a coordinate plane, your x-axis is going to be your n values, so those are like your inputs, and then your y-axis is going to be your a sub n values, or your outputs. So when we take the first 4 terms that we plotted, so we'll go ahead and make like each dash mark in the x direction, or in the n direction represent 1 unit, and each dash mark in the y direction or the a sub n direction is going to be equal to 1 unit as well. So when we plugged 1 into that formula, the output was 2, so that's going to correspond to the ordered pair 1, 2. When we inputted 2, we got that to be 3/4, so that point is 2, 3/4. When we inputted 3, we got 4/9, so that's the ordered pair 3, 4/9, which is about in there. When we inputted 4, we got 5/16, which is about in there. And then if we look, if like our n values were to continue on, where does it look like the terms of the sequence are approaching? Looks like the terms of the sequence are going to wind up getting closer and closer to 0. So that's one thing we're ultimately going to do in this lesson is figure out, do the terms of a sequence converge or do they diverge? And we can determine that by taking the limit as n goes to infinity of your formula here. And if we take the limit as n goes to infinity of that formula, we see that the denominator is of higher degree than the numerator. So if you want to use L'Hopital's rule, that's fine. If you want to use what you know about rational functions and you know that that limit is going to approach 0, that's totally fine as well. And we're going to see just in just a second that if we take the limit as n goes to infinity of the formula that generates the terms of our sequence, if we find that limit is equal to some finite number L, then we can say that that sequence converges to that number. Okay, so the sequence that we found up above, that sequence is going to converge to the number 0. And that's going to be one of the important things that we do in this lesson, is be able to look at a sequence and determine whether that sequence converges or diverges. Okay, if a sequence grows without bound, okay, so that means that when we take the limit as n goes to infinity of the formula that generates all of the terms of the sequence, if we find that limit goes to either positive infinity or negative infinity, then we can say that the sequence diverges. Okay, so again, if we take the limit as n goes to infinity, we find that to be equal to a finite number. That means that the sequence converges. If we find that that limit goes to plus or minus infinity, that means that the sequence diverges. Okay, so these limit laws for sequences, like, I'm just going to have you write them down as like a reference for you in your notes. You'll do this like naturally, like you don't even have to think about these limit laws. You'll perform these naturally whenever you find or take the limit as n goes to infinity of any sequence. So if you have the limit as n goes to infinity of the sum or difference of two sequences, then you can take the limit as n goes to infinity of the first sequence a sub n and add or subtract the limit as n goes to infinity of the second sequence b sub n. You take the limit as n goes to infinity of some constant or some coefficient c times a sub n. Then you can pull c out front and take the limit as n goes to infinity of a sub n, multiply those two results together. If you have the limit as n goes to infinity of the product of two sequences, then you can take the limit as n goes to infinity of each sequence and then multiply those two limits together. Limit law number 4 says if you have the limit as n goes to infinity of the quotient of two sequences, then you can take the limit as n goes to infinity of the numerator, divide it by the limit as n goes to infinity of the denominator. And lastly, if you have the limit as n goes to infinity of some sequence a sub n raised to the p power, then you can take the limit as n goes to infinity of a sub n and then raise that result to the p power. Okay, so again, don't have to memorize those. You'll do those naturally as you work through these problems. Okay, so let's get into the first type of example that we're going to be asked to do in this section. We need to be able to look at a sequence or look at a formula and determine if the sequence converges or diverges. Okay, so What we're going to need to do here is we're going to need to take the limit as n goes to infinity of a sub n, which is like taking the limit as n goes to infinity of n over n plus 1. If you want to use L'Hopital's rule, and this is a candidate for L'Hopital's rule because if we take the limit as n goes to infinity of both the numerator and denominator, it goes to infinity. You can use L'Hopital's rule to evaluate that limit, and this is going to become the limit as n goes to infinity of the derivative of the numerator, which is 1, over the derivative of the denominator, which is 1. So that limit is equal to 1. Because that's a finite number, that means that that sequence converges. Okay, you don't have to use L'Hopital's rule for this. If you want to think of it this way, where you take the limit as n goes to infinity of the end behavior of the numerator, which is n, over the end behavior of the denominator, which is also n divided by n simplifies to 1, so that limit is also going to be equal to 1, thereby making the sequence converge. Okay, so I don't care which of those two approaches you use to evaluate the limit. Either one of those would be acceptable. Okay, so you guys give 2, 3, and 4 a try. Go ahead and pause the video to do that. And then we'll come back and you guys can check your answers against my work here. Okay, so again, if we want to determine the convergence or divergence for number 2, we're going to take the limit as n goes to infinity of this formula, n squared over n plus 2. Again, I'm going to use L'Hopital's rule here because as n gets large, both the numerator and denominator go to infinity. So that's an indeterminate form, infinity over infinity, which means we can use L'Hopital's rule to evaluate. So when I do that, we get the limit as n goes to infinity of the derivative of the numerator, which is 2n, over the derivative of the denominator, which is 1. And as n gets big, that function 2n winds up going to infinity, which means that the sequence here diverges. Okay, number 3, when we take the limit as n goes to infinity for number 3, once again, as n gets big, the natural log function gets large, and the denominator n gets big as well. So that's an indeterminate form, infinity over infinity, which is a candidate for L'Hopital's rule. So I can go ahead and differentiate the numerator, which gives me 1 over n. The derivative of the denominator is 1. So this becomes the limit as n goes to infinity of 1 over n. And as n gets large, that limit goes to 0, which means that that sequence is going to converge. All right, for number 4, we have the sequence a sub n generated by the formula 2 to the n power over n to the 4th power. So when we take the limit as n goes to infinity of 2 to the n over n to the 4th power, as n gets big, 2 to the n power goes to infinity, and n to the 4th power goes to infinity as well. So when I do L'Hopital's rule once, we get the limit as n goes to infinity. The derivative of the numerator is 2 to the n power times the natural log of 2. And the derivative of the denominator winds up being 4n cubed, which, if we take the limit as n goes to infinity of that, that's still of the form infinity over infinity. And I'm going to have to do L'Hopital's rule several more times in order to put this into a form where we're going to be able to evaluate the limit. Now, what I see when doing this is the numerator is always going to become 2 to the n power times the natural log of 2 raised to some power. Because if I use L'Hopital's rule again, the numerator is going to become 2 to the n power times the natural log of 2 squared. But as I keep taking the derivative of my denominator, the next derivative of my denominator is going to wind up becoming 12n squared. The following derivative, the denominator is going to become 24n, and then eventually that denominator is going to wind up becoming a constant. So while the numerator winds up being an exponential, the denominator eventually becomes a constant. So the limit as n goes to infinity of this formula here is eventually going to go to infinity, which means that the sequence here diverges. Okay, for 5, if we take the limit as n goes to infinity, 4 to the n power over e raised to the n power. Like, I know that both the numerator and denominator are going to go to infinity here. So this is a candidate for L'Hopital's rule. It's just that the numerator, like as I take derivatives, it's going to become 4 to the n times the natural log of 4 over e raised to the n power, and no matter how many times I take a derivative, that is going to be an indeterminate form. So what I can do actually with number 5 is I can rewrite that quotient as 4 over e raised to the n power. And 4 over e is going to be some number that's slightly bigger than 1. If I take a number that's bigger than 1 and raise it to the n power, as n goes to infinity, that limit's going to wind up going to infinity, which means that that sequence there diverges. Okay, you guys try 6. So it's not a typo. You have a sub n equal to the sine of x divided by n. Okay, so when we take the limit as n goes to infinity of this formula here, the limit as n goes to infinity does not apply to that sine function at all. So you can think of like sine as behaving like a constant in this particular case. So I can go ahead and pull sine out front and then multiply that by the limit as n goes to infinity of 1 over n. We know the limit as n goes to infinity of 1 over n is 0. So essentially this is like taking the sine of x and multiplying it by 0, which makes the value of that limit equal to 0. And if the value of that limit is finite, that tells me that the sequence converges. Okay, so that's one of the important things that you'll need to do with sequences is determine whether they converge or diverge, and to do that, we take the limit as n goes to infinity of that formula. Okay, we'll get into some additional stuff in part 2 of this video.